This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Moves. So the alternative description I mentioned to you that is sometimes used for astrophysical problems that I know, where x is the position of a particular particle, and x naught is where the particle was at t equals naught. So now we're going to, I'm going to work out some numbers for you in a minute, but we're going to assume small volumes of fixed mass of particles in the fluid flow are in near thermodynamic equilibrium. That's to say, all relaxation times, for example, translational relaxation times or vibrational or rotational relaxation times, are small compared with flow times. And that introduces the concept of the mean free path. How many of you have heard of the mean free path? I can't believe it's not anybody. Nobody has heard of the mean free path. So the mean free path is the distance a molecule or a particle travels before it suffers a collision with another particle. So that's lambda. And so the collision time, the time for the next collision, is the distance divided by the average speed of molecules. And we're going to find out the average speed of molecules is close to the speed of sound. So lambda over c bar is the time for a collision. And in order to reach thermodynamic equilibrium, that time has to be much, much smaller than flow times. And what's a flow time? It's the distance, some characteristic distance of the fluid that the fluid flows through, divided by the velocity of the fluid. So if a body is of order, has dimensions d, lowercase d, then the flow time is of the order of d over u. And we're going to say that that time is much, much longer than the collision time. So static variables such as temperature, pressure, internal energy, enthalpy, and the pressure are then thermodynamic variables connected by the equation of state of the particles. So you're saying essentially that the fluid remains in thermodynamic equilibrium, and you're going to be in great trouble if you're doing hypersonics, and the flow time is comparable with collisions, because then you won't be able to use thermodynamics in the way that we are going to use it. All right, so now let's make some estimates. So how do you do it? So the first thing you do is that you imagine a molecule of some characteristic radius r, and now you suppose that there are all these molecules in space. But what I'm going to do is that if all of their characteristic dimensions are of order r, I am going to make a disk on one particle of radius 2r and leave all the other particles as points. So this particle with a disk of diameter 2r is now going to sweep out a volume. And how big would that volume be? Well, in unit time, it'd sweep out a volume which is pi times RC squared, that's the area of this disk, multiplied by the speed that it's traveling, which is basically c, the average speed of the molecules. So in unit time, it'll sweep out a volume pi RC squared times c. So how many collisions with points would there be? Well, in that volume, there are lowercase n molecules per unit volume. We're going to say that P is nkt, and we're going to work out how big, come on in. We're going to work out how big n is in a minute. So in unit time, the volume swept out is pi RC squared times c, and the number of particles in that volume will be the number per unit volume, number of particles, but they're all regarded as single points. So the number of collisions in unit time will be n pi RC squared times c. So if you have that many collisions in unit time, how long will it take for one collision? It'll be that number divided by 1 divided by that number. So the time for one collision then is 1 divided by n pi RC squared c, and that is going to be the mean free path, which is the distance a molecule on average travels for one collision. That distance divided by the velocity that the particle has will be a time for one collision. Right? So we see that we have an estimate here of the mean free path. Lambda will be, so they've both got c in the denominator. So lambda will be n pi over RC squared. So now how big is n? How big do you think n is? How many of you have ever worked out how many molecules there are per unit volume in air at standard temperature and pressure? You have. Great. In high school chemistry. Okay. And what do you think the answer is? There's the number there, 2.3 by 10 to the 25. So how did I work it out? So I worked it out by saying, here's the pressure, and the pressure is nkt. And I know that Boltzmann's constant is 1.38 times 10 to the minus 23. So I put into this equation, I'm going to solve for n. I'm going to put in the pressure of 1 atmosphere, and 1 atmosphere is 10 to the 5th newtons per meter squared. So I'm going to put 10 to the 5th on the left-hand side, and I'm going to put for the absolute temperature about 300 degrees K, 23 degrees Celsius. And if I do that, with K, T, and P, I get N is 2.3 by 10 to the 25th. So in this room, as we speak, there are 10 to the 25th molecules, 10 to the 25th molecules in 1 cubic meter. 10 to the 25th. So what is the mean free path? It's 1 divided by pi, so that's 2.3 times 10 to the 25th. Pi is about 3. Now, what is the radius, the collision cross-section? Well, you know that the diameter of is about an angstrom. That's 10 to the minus 8 centimeters. So that's 10 to the minus 10 meters. And so I've got 2 of them, roughly speaking, for the radius of my, I got 2 of them. So that's 2 by 10 to the minus 10, and I'm going to square that. So that's 4 by 10 to the minus 20. And the answer is lambda is 3 by 10 to the minus 7 meters. That's how far. So it's a very small fraction of, well, we have millimeters, that's 10 to the minus 3 meters, and so on. So this is about 3 by 10 to the minus 7. Now, what is the average spacing between molecules? How big is the spacing between them? Well, we're going to say that if the average spacing between molecules is of the order ds, so the volume is ds cubed, roughly speaking, and in that volume I'm going to have one molecule. So I have n molecules per unit volume, so n times ds cubed is going to be one molecule. Then what is the average spacing between molecules? Well, if I take the cube of 1 upon n, the cube root, I mean, of 1 upon n, so that is, yes, 23 by 10 to the 24th, and I take the cube root of that. The cube root of 27 would be 3. 3 3s are 9, 3s are 27, so 2.3 is near enough to 2.7. And the cube root of 10 to the 24th is 10 to the 8th. So the average spacing is 1 over 3 by 10 to the 8th meters. This is how I worked it out, and the radius of a hydrogen atom is about a half an angstrom, because the diameter of the atom is about 1 angstrom. So for a molecule, the radius is about 2 of those, so it's about 1 by 10 to the minus 8. So that's how I worked it out. And so what is the average distance divided by the cross-section? And the cross-section, if you put those in, ds is 1 over 3 to the 8th, and rc is 1 over 2 by 10 to the minus 10. The answer is 100 over 6. So so the distance between molecules is very large compared with their collisional cross-section. 100 over 6. It's about 16. And lambda, well, we worked out what we could take lambda divided by ds, and lambda divided by ds turns out to be about 100. So the mean free path is much, much longer than the distance between molecules. Much, much longer. About 100 times larger. So the ratio of lambda, the mean free path, to the spacing between the molecules, to the collision cross-section, radius of the collision cross-section, is about 10 to the 4th to 100 to 6. Or, if you divide them all by 3, 3,300, 3,300, this is 33, and this is 2, and so the ratio is about 1,600 to 16 to 1. And the collision time is the time for the average molecule to travel between collisions, and the average length is 3 at room temperature and pressure is 3 by 10 to the minus 7 meters, and the average speed is about the speed of sound, as it'll turn out. So that's about 300 meters a second, and so it's about 10 to the minus 9 seconds. So the collision time, the time for one collision in the air here today, is 10 to the minus 9 seconds. So it's a very, very short time. Yes?
Can you please repeat how did we find ds?
ds, yes. ds I found, let's see now, can I? So I said that the average spacing between molecules is ds. So the volume that one molecule occupies is ds cubed, roughly speaking. That's the volume, times the number of particles per unit volume. So that number of particles per unit volume times ds cubed has got to be equal to one molecule. So there it is there. N ds cubed is equal to 1. Knowing what n is, I therefore know what the average spacing is between molecules. All right, and ds is about 1/3 by 10 to the minus 8 meters. Very, very small. Now, so that's a very, very critical idea, that we're going to say that as this fluid moves around, even though it's going to go at twice the speed of sound, we're going to say that the fluid, that takes time for it to get up to twice the speed of sound, and that takes time which is much longer than the collision time. And therefore, the fluid doesn't know that it's moving. It remains in thermodynamic equilibrium. So that's a key idea. You absolutely must understand that everything falls apart if I make a hole that is so small that it's comparable, for example, with the mean free path. Then that tiny hole, even though I've got a vacuum on the other side, if the hole were that small, it wouldn't be a good approximation to talk about something being in thermodynamic equilibrium, because it wouldn't be. And you'd have to use different physics. You'd have to use the Boltzmann equation to work out how much flow there is through that hole. All right. Now, the next idea in the application of thermodynamics to compressible flow is that we need an additional energy term. Not only do we need the internal energy of the particle, we need its kinetic energy per unit mass. And the kinetic energy per unit mass is 1/2 ui squared, where I'm going to use frequently the tensor notation that ui times ui means each component, it means ux squared plus uy squared plus uw squared. The three components of I, 1, 2, and 3, u1 times u1 is u1 squared plus. So when you see the suffix repeated twice, ui, when ui squared is ui, when you see that suffix repeated twice, you have to sum over all three values of the index, right? So the kinetic energy, 1/2 ui squared per unit mass, must be added to the internal energy. And because it's affected by the pressure in a different way from the internal energy, in a sense it's another variable and requires additional equations. And basically you're going to require the momentum equation. So to describe the change of state now requires the conservation of mass, the conservation of momentum, the conservation of energy, and the equation of state. Particularly, and I've talked to you about a canonical equation of state, like H of S and P. If I know H of S and P, I can find T, and I can find V, and I can find everything out that I want to know about its thermodynamics. If I have H of S and P, I know P, and therefore I know, and if I can work out the specific volume, then I can work out the density, and if I know H and the density and the pressure, I know the internal energy, I know everything, right? So that's a canonical equation of state. Now, how many equations do we have? Well, if we have, and what are the unknowns? If we have conservation of mass, as we're going to see, introduces rho and the density and the velocity. So there are, that's one equation. And now if I have the momentum, even if it's an inviscid fluid, let's talk about an inviscid non-heat conducting fluid, I'll have the momentum requires the density, the velocity, and the pressure. And because it's written down for each component of the velocity, there are 3 momentum equations. And then the equation for energy involves the internal energy, the pressure, the velocity, and the density. And that's one equation. And lastly, we need an equation of state and a canonical equation of state. So we have H of S and P, for example, and that's another single equation. So we have 1, 2, 3, and 3. We have 6 equations. What are the 6 unknowns that we can solve for? They are rho, E, P, they're 3 unknowns, plus the 3 components of velocity. So that's 6 equations we need for 6 unknowns. And if the fluid is viscous and heat conducting, we need some more equations. Viscous, we're going to need we need an equation relating the viscous stress. We have to put the viscous stress into the energy and the momentum, and we have to put heat conduction into the energy equation, and we'll have to use Fourier's law and a law for the viscosity. So, all right. So now I'm going to get for you these conservation equations, and you've all seen them before, but it can't hurt you to see them again. And if I asked you this question, how many of you would know the answer immediately? So here's my question. I have tea leaves in a teacup, and I stir it. Where will you see the tea leaves? When you take the spoon out, where will the tea leaves be? Beg your pardon? Louder. Say it louder. In the center. And now, if I asked you why, how many of you could tell me why? In a heartbeat. Nobody. Good God. Well, I'm going to show you how to work that out in a heartbeat. So, we're going to do the equations of motion, and they don't take much, but they do require you to sit on your tail and think. So, what would conservation of mass be? It means that if I had a fixed volume of particles, and not a fixed volume, a volume of particles, and the density of the particles could change. But I keep track of the same molecules, then it would say that the derivative following, so this is the total derivative, d dt. It means following a fixed set of particles. That's what that means, d dt. Now the volume could change with time, and I'd have to integrate over that volume, rho dV, and I'd get the total mass in the volume but I'm not changing any particles in the volume. So it says that following that set of particles, d dt of it, the total derivative of it with respect to time, would have to be 0. Is that clear to everybody? Now, in order to progress that, so here's the volume at time t, and at a later time, just a little bit later, here's the volume, which is bigger, let's say, than it was at time t, and this is the volume at t plus delta t. So what has happened? We can work out the mass that we had at time t. The mass at time t is the integral over the volume at time t, rho of x and t dv. What about the mass at time t plus delta t? Well, that would be the integral over the volume at t plus delta t, which is this bigger volume here. Rho at x and t plus delta t dv. Now what you do is you can say, all right, how do I relate this volume at t plus delta t and the things at t plus delta t to what they were at the time t? And so you can see that what I'd have to do is I'd have to subtract the mass that would be in this volume here, delta V1, and I'd have to add the mass that would be in this volume, delta T2. Now, it's easy. So if I had a little element on the surface here of element delta S, how big would this volume that the fluid swept out would be? How big would that be? Well, it'd be the velocity times delta T, that's the height, times the area, and the area would be delta S, and the perpendicular height would be u dot n. So the perpendicular height of this little volume would be the area times the perpendicular height would be the volume. So the slant height is u delta t. The perpendicular height would be u dot n delta t, and I have to multiply that by delta S, and I'd get the right volume. So I just sum that up for all these delta S's, and I could do that. And you can see, and if you're careful about it all, you can work all this out. And you can see that these volumes, delta V2 and delta V1, one of them is minus, but the n, so let's just remind ourselves, the n is the outward normal always. So the outward normal here is this direction. So the slant height of this one will be u delta t, and the volume that I've got to subtract would be u delta t dot minus n, because minus n would be in this direction. And when I do that, you can add all of these up, and you get a flux over the original surface. So that's how you do it, and then dm dt is by definition the limit as delta t goes to 0 of the mass at t plus delta t minus the mass at times t divided by delta t. And that's what I mean by d dt of the integral of rho v of the volume, which is a function of time. And that has to be 0. And when you do all of that, you can quickly show to leading order that equation reduces to the rate of change of the mass in the volume initially at time t1 plus the flux of mass out. And that's obvious that the mass can't change, but the mass in the volume will go down if there's a flux out. So this conservation of mass with the moving volume gets replaced by a control volume, a fixed volume. And for a fixed volume, and by fixed I mean that it's the volume at T1, so it's the original volume. So I work out the mass in there, and then the mass in that original volume at a later time, and divide by delta t and take the limit, and that is d dt of this quantity here. And now you see this volume is the original volume, so the volume doesn't depend on time. And so I could take this, so this is an integral which now if the density depends on time, then this integral will depend on time, and I get something which doesn't depend on dimensions anymore, lengths. It's only a function of time, so that's why this is a total derivative, d dt. Whereas this is now the flux out of a surface of the original surface of rho u dot n ds. Now that is so important that the original d dt of rho dv can be replaced by this total derivative of a volume that's fixed. So it's not the volume that moves with the particles anymore. It's the original fixed volume, the control volume, and this is the surface of the control volume. For how many of you is that very familiar? Nobody? Nobody. Good God. Okay, then if there's one thing that I'm going to leave you with, it's to know this standing on your hands. If anybody asks you about the conservation of mass, you can say that it's expressed by this conservation law. The rate of change of something inside the volume plus the net flux out is 0. You absolutely must know that. So there it is in words, the rate of change of mass in the volume plus the net flux out is equal to 0 in this case, or if it's some other form of conservation law, it's a source term. It's a source term. Now, one more thing which will make this very familiar to all of you. The integral of u dot n ds is, by Gauss's theorem, the integral over the volume of the divergence of u dv. Is that familiar to all of you? Yes? Good God. You must be honest with me. I'll be very upset if I think that you know something and you don't. You have heard of Gauss's theorem, right? In mathematics. I hope you could all derive it. I fear that's probably not true. Okay, so I'm going to change that surface integral, u dot n ds, to an integral over a volume for every little volume For every little volume, I'm going to work out the divergence of u. So I have u at x, and I'm going to take it as du dx plus dv dy plus dw dz. All right. And so if I change back in this equation, rho u, just imagine that as another vector u, a dot n ds, around the surface, I can change that to an integral over the volume of the divergence of A dV, where A is rho u, right? So now, if I do that, this integral over a surface will be the same thing as the integral over a volume. And so I can put this and this term together. So let's do that. And so I have d rho dt plus the divergence of rho u, the integral of dv equals naught over the original volume. But what if I chose a different volume? I'd still have to satisfy it. I have to satisfy it everywhere. So let's suppose anywhere in this volume, these terms inside, integrated over the volume, were not zero. Then I'd choose my volume where they're not zero, and I wouldn't get zero on the right-hand side. So what's that tell you? It tells you that everywhere, this integrand, because v is arbitrary, everywhere this thing must be zero. So I've suddenly gone from an integral form of a conservation law to a differential one. d rho dt plus the divergence of rho u equals naught. How many have seen that before? Come on, all of you have seen it before. If you've done fluid mechanics before, you know that the conservation of mass is the partial derivative of rho with respect to time plus the divergence of rho u equals naught. What would happen? What would it be if density were constant everywhere? What would that equation become? Div u equals 0, which tells you that for an incompressible fluid, the divergence of u has to be 0 everywhere. You've seen that in incompressible fluid flow, I don't doubt. So the compressible equation that we're going to need to solve is d rho dt plus the divergence of rho u equals naught, or what is actually more useful frequently is the integral form of it. The rate of change of the mass in the volume plus the net flux of mass out through the surface of that fixed volume must be equal to 0. All right, so we can go from that grand integral statement down to a differential equation. However, what if one of these variables is not differentiable? Like the density is not differentiable. When would the density not be differentiable? You tell me. Anybody know?
There is no uncontinuity.
If it's not continuous. All right. So in what circumstance would it not be continuous?
In moles, for example.
What if you had a shock wave? if I had a shock wave, the density here is rho 1 and the density here is rho 2, and the shock wave in classical form is a discontinuity. But the integral equation doesn't care about the fact that it's not differentiable. The differential equation would. So the conservation law in integral form is always correct. The differential form is usually correct. Now, what about another quantity that will be familiar to all of you? The conservation of charge. Electrodynamics. Conservation of charge. What is the conservation of charge? What is the equation, one of Maxwell's equations for the conservation of charge? What is it? It's in the same form. The charge is conserved, and so the rate of change of the charge density plus the divergence of the current out of the volume, the divergence of the local current, is equal to 0. Well, you can derive that. That's Maxwell's equations. All right. So now I'm going to do momentum. This is going to be terribly important to us. We have to know something about momentum. So let's talk firstly about a fixed set of particles. Then all of you will know that for a fixed set of particles, the rate of change of momentum of each particle is the net force on each particle, right? So this is Newton's law. So if I have a particle, I change its momentum. It's really the force is the mass times the acceleration, but that's the change in the velocity divided by the time, and the the net force is the change of momentum of each particle. But if you sum over all particles within the volume, the internal forces between this particle and this particle, they collide, and they've got a force on them, when that changes the momentum of this particle. But this force is exactly equal and opposite to this force. The force on one is equal opposite to the force on the other. So if I add them all up, they all cancel in pairs. And so the net force acting is the sum of all of these external forces. I'm calling them external forces because they won't be all balanced by the opposite force on the boundary. On the boundary, one is going to feel its neighbors before it actually hits it. And those external forces, for example, the pressure, won't be balanced in pairs. Thus, the net force acting is the sum of the external forces acting on all the particles, for example, gravity, because they all acted upon by gravity, plus the short-range forces on the boundary. So we can write for the ith component of the momentum and for an inertial coordinate system, so that ui is in an inertial frame, otherwise we can't write down Newton's law, or at least not in the same way. Then it says that if I look at the rate of change of the momentum of all of the particles, so we're talking about fixed mass of all of these particles, then on the boundary there are forces between the particles that are not balanced, and they're called the stresses, and I'm going to call the ith moment of the ith component of the force on the boundary is pi I ds. And then there's another force, rho Fi, where Fi is the force per unit mass, like gravity, like G. And rho is then Rho dV is the mass dm. So dm times F is the amount of force for rho dV, for a mass dm. So that must be true, where Fi is the external force per unit mass. For example, F is equal to the gravitational acceleration g. And pi I is the force per unit area, or the stress. So it's the force per unit area multiplied by the element of area ds, summed up over all of the boundary. Pi I ds is the component of the force per unit area in the ith direction on the infinitesimal surface where the normal is n. And so you say, well, my goodness, this is complicated. But it's not. Now, the force in the ith direction, the force per unit area, or the stress per unit area in the ith direction on the surface, delta S, depends on the direction of the normal. So that's why I've put in brackets there n, and it's the vector n, is the component of the stress in the ith direction on an infinitesimal surface where the normal is n, which is a function of x, y, and z on the boundary. On this surface, the component of the force in the ith direction depends on the actual direction of n. For example, let's take the pressure. The pressure, for an inviscid fluid, the pressure acts equally in all directions. And so the force in an inviscid fluid, so now let me make sure you understand this. So here's a little force. So what's the force on the fluid? So here's the normal n, and the pressure acts equally in all directions. So from this fluid out here acting on this surface, the force will be the pressure times the area, so that's P delta S. And what will be the direction of the force? Minus n. And that would be the force that would act. How would I work out the force in the ith direction, in the x direction, for example? What would I do? I want to get the force in the ith direction. What would I do? That's a unit vector, right? So it's this vector, which is a unit vector, times this vector, which is a unit vector. So it's the cosine of the angle between them. So if I want to work out the force in the ith direction, I need to work out, so the force I got, this is the force in the minus n direction, but I need to work it out in the ith direction, so I need minus n dot I, or n dot I times that minus. All right. So now that's a very important idea, and what you can see is that that force in the ith direction, so there's what I've just written down is written here, minus P delta S n dot I. And so the force in the x direction, this n dot I is also the x component of n. Ny, of course, is perpendicular to it. Nz is perpendicular, so that's just n, the x component, so it's minus Pnx. So that derivative the rate of change following these particles can be written as, for a fixed volume, the rate of change of rho ui, the momentum in the volume, where the volume is now fixed, plus the integral of rho ui, that's the momentum per unit mass, uk nk. So this is u dot n, is the net force in the ith direction. So now that is, I've said, extremely important for applications. If we're going to work out a rocket, for example, we're going to have to work out both of these terms. What is the flux of mass in the ith direction across the boundary, u dot n ds? What is the net force in the ith direction, because we want it to actually be going up? So, and we're going to say that in words. You must know it in words. The rate of change of momentum in the volume in the ith direction, plus the net flux out, the net flux of momentum in the ith direction out, is equal to the net force acting in the ith direction. And you would be amazed how many real problems are solved by writing that down. If you're a consultant when you leave here, unless you know this like the back of your hand, you will flunk. But if you do know it like the back of your hand, then nobody will talk you out of it. And there'll be a whole lot of people sitting around the table and they say, we don't know what happened. And you'll put your hand up and say, that's what happened. And I can tell you that's for real. That is for real. When the Titan IV blew up on the pad, I became absolutely certain that the failure was in the computation. The mesh was too large because they didn't get the right answer. Why? Because I did this sum and said, you didn't get the right answer because I can tell you that if you'd got the right answer, you would have got the answer from this equation. And I knew the mass flux. I knew what was going on. And I knew. And I can tell you what happened. Well, I have lots of war stories, but I could tell you sometime, if you ask me, I'll tell you what happened, why the thing blew up. But I can tell you that the CEO called me up and said, I am not going to test the next one unless you can tell me it won't blow up. And I said, well, I can tell you that it won't blow up. I can't tell you that it won't blow up, but I can tell you that it won't blow up for the same reason. And so he said, that's good enough for me. So he authorized the test. The first one had been on the front page of the New York Times when it blew up. And he said, I'll lose the company if the next one fails. I'm not going to press the button until you tell me it won't blow up. Until you tell me it won't blow up. You can imagine, sweat is running down your back. And you say, I can't tell you it won't blow up, but I can tell you it won't blow up for the same reason. And I have a photograph on my wall from, oh, good God, what happened here? Did I do something catastrophic?
Yeah, I think it blew up.
I'm sorry.
No, that's okay. It's a good chance to show my touch typing skills. Hopefully I didn't show my
The mere
touch
passage of time did me in. Is that what happened?
typing. I'm not sure. Oh wait, you want the lectures, right?
Yep. Four.
Yep. And just get you back to where we were. Oh no, here we were.
Right.
A bit.
Yeah, thank you. Thank you. I'm so sorry. All right. So now, if you have this equation, Gauss's theorem can be used again. You can see that I can replace this rho ui, uk, nk by some vector a dot n, and so the